Okay, I think we'll get started. All right, thanks everyone for joining us. This talk is on OpenStack architecture and deployment at Target. I'm Mark Christensen, principal engineer. I've been at Target for about 3 years now, and I've been doing OpenStack for about 6 years before joining Target. Also did OpenStack at another Minneapolis-based retailer. And with me is Ryan Tidwell, lead engineer on the project. How long have you been with us now?
It's like a year and a half.
Okay,
almost.
yeah. So Ryan's been with us for about a year and a half. We're really glad to have added Ryan to the team. Some of you may know him from the work he's done on the Neutron project. Okay, so if you're from the US, I'm sure you know all about Target. You probably live within 10 minutes of a Target, and you're probably there more than once a week. But for those of you who don't know a little bit about Target, Target is a value retailer in the US. We have 1,829 stores, which I just learned is about 240 million square feet of retail space. We operate 39 distribution centers across the US. We have 350,000 employees, mostly in the US, but we also do have offices in Bangalore, India, that do provide support for us around the clock. And Target.com is the 4th most visited retail website in the US, with more than 26 million unique visitors on average each month. So retail these days is very competitive. In the last decade or so, there's been a lot of disruption, and so as retailers, we really need to innovate and move fastly to compete. So we've been doing that in a number of ways. Moving from sort of the traditional suburban large format store to more innovative store formats, more urban, smaller, we're on college campuses, things like that. Really working to improve the customer experience too, and we do that through things like innovations we've done in point of sale, self-checkout, things like that. We've introduced a number of convenient things, order pickup, drive up, where you don't even have to get out of your car, you place your order, drive up to your Target, they bring it out. That really works out well in some of these urban locations. Say you're in New York City, hard to find parking, right? You just drive up, you get your stuff, you go. Restock, low fee for all those household essentials. You order it, gets delivered the next day, small fixed fee. This year we acquired a couple of companies, Shipped and Grand Junction. Grand Junction is kind of a shipping logistics company. It helps us to determine the fastest way to get an order to you. So what that really allows us to do is shorten that time from order to you getting your product. So we go from multiple days down to day and same day in some instances. Shipped is our same-day grocery delivery service, which is really cool. If you're near a Target, I suggest you try it out. I've recently signed up, and it was really a great experience. You get a personal shopper. They get all your stuff. They'll let you know if they need to substitute things, and then they bring it to your door. It's really awesome. And then Target has lots of very popular brands that people love. Okay, so to compete, right, we have to innovate, and we have to innovate in our stores. We have to innovate online. We have to innovate mobile. And so in the last few years, Target has gone through some really transformative changes, right? Really adopting open source broadly. All of our teams have gone agile. And one of the main things is everything is an API. Everything we do, there's an API. So OpenStack is an important enabler for that. So going back to before I started, 2014, before OpenStack made its appearance at Target. Target has 2 production data centers. Back then, everything was kind of centrally managed, a mix of blade and rack mount infrastructure. Because of the nature of those data centers, it was really a lot of low-powered, kind of low-end, low-power Intel. So the 2630Ls, 384 gig of RAM, and a very traditional 7K, 5K, 2K, layer 2 broadly across the data centers. We did have bare metal and virtualized workloads, but still, this was a very traditional process, so it could take weeks to get even a VM. You put in a request, it goes through an approval process, and then somebody goes and provisions that, right? We also have utilized third-party hosting for some of the aspects of the technology. And then we have certain mainframe applications as well. So in 2015, we had our first OpenStack deployment. It was deployed into that existing hardware infrastructure. Utilized a vendor-packaged Icehouse release, native Neutron, GRE encapsulation, pretty standard configuration for back then, right? Deployed with PackStack, and virtually no configuration management. So it was kind of a somewhat ad hoc, but it was kind of an experiment, right? So that was okay at the time. And Ceph for storage, that was Ceph with HDDs. But that was pretty good. It was 2 guys who wanted to give OpenStack a try, deployed it out, and the uptake was really fast, because obviously the comparison between what you can do with OpenStack, you get your infrastructure now versus the old process, is very popular. So the uptake amongst our developers was quite rapid. That team grew pretty quickly because OpenStack was growing pretty quickly at Target. So went to about half a dozen engineers in that first year to start building and growing. And I joined about halfway into the year after that initial deployment. And that team provides both the engineering and end user support. I'm going to let you watch the clock for me because sure.
Okay.
All right, so initially, the initial usage of that was mostly around deployment, or development rather. Mostly Linux, but we also brought some Windows workloads in there. That mainly supported our point of sale development efforts. And we were mostly internally facing applications. What I mean by that is it's nothing that is a real-time interaction with our guests at our stores. So it was supporting more back-end kinds of things, inventory management and things like that. So that environment grew pretty quickly. And as of now, in our 2 production data centers, we have about 150 hypervisors in each. We also have a development region. We have another facility on our campus where we call that a dev region. And a lot of the developers do their initial work and deployment in there and then move to the production regions. In all, that's about 10,000 cores. And in that dev region, there have been about 400,000 VMs over the lifetime of that. In prod, about 350,000 have been deployed. And we've got about 13,000 plus VMs currently active. So as I said, we started with Icehouse, and we've gone through 2 live upgrades in place, Icehouse to Juno, Juno to Kilo. And those were really successful, and if you had done upgrades back in that Icehouse, Juno, Kilo, you know that it could be fraught with problems, and so really proud of our team, really did a great job in doing those upgrades. Those regions are still all operational, but they are at Kilo, and we're looking at sunsetting those and not moving beyond Kilo in those regions. We also started out with non-HA routers. We transitioned everyone to HA, and over time needed to scale Neutron quite a bit. So we put in faster machines, scaled out. We've got 5 Neutron nodes in each production data center. I think we have 12 in dev.
Yeah.
Right. Yeah. OK, so storage, as I mentioned, we started with HDDs. Around our peak holiday season a couple of years ago, we were seeing some real performance issues with that. So went through, replaced all those HDDs with SSDs, really brought up our performance, and that's worked out really well. Started with Ceph Hammer, upgraded that to Ceph Joule. That remains at Joule. And that's used for both Nova Center block storage as well as Swift-compatible object via the Rados gateway. And we have about a 1 petabyte raw storage in each of the 2 data centers, 2 production data centers. OK, so that first generation was really great, but it also had some glaring issues. One of them was networking. Networking was an issue. As I mentioned, we had to scale it, but we also had some stability issues around that. The other thing is that the way that we did our external networks, we ended up with, I don't know, like 8 external networks or something like that. So our users had to, start to understand, where are we going to land our things and which external network do I need to attach this router to? Where do I need to allocate my FIPS from? Things like that. And we wanted better performance. We found at best on that hardware and with that Neutron infrastructure, we could get maybe 4 gigabits per second to a VM. We wanted to continue with adequately performant. We don't host really high I/O workloads in our regions, at least not yet. And cost effectiveness was important there, so that was a consideration. We wanted to make sure that we could do fast deployment and redeployment. We wanted to make sure everything was config managed from start to finish. And we also wanted to do some things. I mentioned, everything was pretty much internally facing on that initial, in those initial regions. We wanted to bring in internet facing. That means guest facing, real-time kinds of interaction with guests, and to be able to host both PCI and SOX workloads, so we can actually start to bring in some of our payment processing and financial workloads. So we still have some power constraints in our data centers. We have re-engineered things a little bit, so we can pull a little more power in our rack, but we're still a little bit constrained there. And then one of the other things is that from up on high came down that We're only doing blades. We're not doing any rack mount. And so that has an implication on our storage in that we couldn't do Ceph. And we love Ceph. Ceph really works great. And so we needed to find an alternative. So at the same time, we were looking across all of our hardware infrastructure and how do we do things faster and more efficiently in the data center. And so one of the things was to standardize as the unit of expansion within a data center is going to be a rack. That rack will have a standard configuration that we use across pretty much everything that lands in the data center. And so what we ended up with was we were able to move away from the low-powered CPUs to more high-end. So that rack consists of 2-blade chassis. So we get 32 blades per rack. They're the dual Intel 2690s, 1.5 terabytes of RAM each. So that gets our density up and it gets our performance up per rack. And then one of the major changes we made was in our networking architecture. So we went from what was fairly flat L2 to a spine leaf topology. So that means L3 to the rack. There's no L2 that spans racks in the fabric. We deploy with a private network. So within the rack, there are 3 separate VLANs, 3 separate IP networks to the top of rack. One is our private operations network. That's where basically the control plane runs. So the controllers talking to the hypervisors doing their storage, things like that. There's a service network. That's the routable network that both supports the incoming APIs and Horizon, things like that, externally routable, as well as just for all of the hypervisors, because that private network is not routable outside of our regions at all. It's completely private to the back end. So we have a service network for our hypervisors that need to go out and get DNS or whatever. So those are, for the most part, egress only from an IP perspective. And then we have a SNAT network where our network address translation for the VMs occurs, and that's on a separate VLAN, lives within a namespace on all of the hypervisors. And we'll get into that as we talk a little bit more about the implementation of the network. So given some of the performance issues and the fact that we wanted to go to get away from the centralized Neutron nodes and go to a DVR, distributed routing model, we did make a decision at the time to work with or to look at vendor SDN solutions. And we went through that process. We evaluated a number of them. And we did make a final decision, licensed that, and we have been operational with that. And that worked out really well. It was pretty much plug and play. We got that up and running really quickly, and it really delivered for us on performance and on the DVR. Not perfect. There are some constraints that vendor solution puts on some of the semantics, the way that it maps into Neutron, right? It's not quite the native thing. So for instance, right, we can't attach 2 routers to a single network. And while normally we don't need to do that, there are certain use cases where that's important. So we've had to work around a few things. All right, so storage, I said we couldn't use Ceph, and so we had to decide, well, what are we going to do? And as you recall, there's this broader look at how are we doing the infrastructure within the data center. because we need to support not just OpenStack, but with essentially the same configuration, other virtualization platforms that we run and things like that. So what we ended up with was dropping in, along with the 2 chassis of blades, there's a storage appliance within each rack. And so we use that for Nova and Cinder. It's NFS to that appliance. But one of the things that came out of that was that those are independent. So we're not doing I/O, storage I/O across from rack to rack. And so the way we did that is we ended up making a rack an availability zone. And we turn off Nova cross AZ attach. So we weren't too worried about that at the time because we were also using some tools that were the intention was that developers would use those. It wouldn't necessarily be fully self-service within OpenStack for developers that there would be tools that would kind of abstract away some of these details from them. That didn't fully pan out in the time frame that we expected, and so this constraining our users to really have to understand those AZs has caused a little bit of pain. So we can't live migrate between racks, and so we've had a few problems where we'll fill up the storage on a rack, or we'll fill up compute, and it becomes a bit of a hassle. Okay. So what did we decide on for deployment? We considered for a while, and ironic really seemed to be a natural thing, right? Use ironic, you're using all of the same OpenStack APIs that we use all the time, same command line stuff. We can use that for actually building our regions. So we started out with OOO, from a vendor implementation of OOO with Mitaka. So we were able to move up a few releases. But at our scale, we determined that OOO wasn't quite the right model. If you're familiar with OOO, basically it's a heat stack, and it's one heat stack that basically defines your whole region. And so you go to do an update, and you're doing updates across every node in that region. That made us a little nervous. We ran into some problems. That stack update might fail, and then recovery was kind of a hassle. So what we ended up doing was following a similar model, but we took it to, we do one heat stack per node, so they're all now independent. And so it's basically just and we have some wrappers around it, but it basically is just a OpenStack stack deploy compute node 5, right? And it goes out and brings it up, hooks it in, and so within 20 minutes, we can have a hypervisor up and online. And then it's easy to do that. We can do that in parallel. We build our own dib images. We've modified the disk image builder a little bit, so moving away from kind of a lot of the shell stuff to Ansible. So that's really made that's worked out really well for us. All right, we use Chef presently for config management, and that's mainly because Chef was already pretty well entrenched at Target. We had the tools around that, so and that works out pretty well. So when we do that, stack deploy of a compute, everything the node comes up, it's pre-configured. It configures the disks. It actually then goes and registers the node with Chef. Chef bootstraps and all of the configuration happens, and so it's completely hands-off from start to finish on that deploy, and you end up with a completely functional node in the end. We've been moving to containerize the services. Right now, that's limited to a subset of the control plane services, but we have gained a lot of insight into that. And so in our next deployment, which we'll be talking about, we're moving to containerize everything. We moved initially when we deployed our second generation, that was on a vendor OS, and we've transitioned now. We're completely open source. We're on CentOS with RDO, and we're actually moving from RDO on some of the projects in our generation. In our second generation, we've moved some of our projects away to actual Upstream, Horizon being one of them. And we're continuing to do that in our next generation as well. We utilize Console and Vault, HashiCorp Console and Vault. We're on the Vault side right now for secret management, but we're also planning to use Console more for service discovery and some of the configuration setting management. We have Jenkins and Drone around CI, and then we have a bunch of other tools, GitHub, Enterprise, Artifactory, things like that we use. How are we doing for time? Okay, so the second generation, we've got about 600 hypervisors. So that means upwards of 32,000 cores at this point. We're adding about 2 racks worth per month, so about 64 hypervisors. We've spun up 180,000 VMs in less than a year since these have gone live, and we have more than 13,000 VMs currently operational. We predominantly are using Telegraph to collect metrics. And we send those metrics as well as our logs to a Kafka topic. And those are picked up by some internal aggregation services that we have. We use Grafana for metric visualization, both Graylog and Kibana for log viewing. And there's some other tools within Target that are available that we haven't really fully started utilizing. One of them, for instance, is real-time stream analysis, where we'd be able to send those metrics and logs and then have various rules that would look at them in real time and then do various things, trigger alerts or whatever. So our current team, we've got about a dozen engineers in Minneapolis. We've got 4 in Bangalore, India. They do support, when we're sleeping, thankfully. And we've been really working more closely with our enterprise and storage, enterprise storage and networking teams as we move forward. So, what comes next? So our second generation is worked out really well, but I mentioned some of those pain points, right? Like the AZ thing. And I also talked about how we had these tools that we expected that were going to kind of abstract away how developers interacted with various platforms, not just OpenStack. So we have made progress on that. So we have something called the Target Application Platform that provides CI, configuration management, service discovery, all of these things, and then deploys applications. And that really, for the applications that are starting to use that, it really hides where they land. And so when they use that, they could actually and there's some ability to direct it, but your application may land on OpenStack, it may land in Kubernetes, it may land in a public cloud. but we're trying to offer one view of how applications are developed and deployed. And so that informs us in what does OpenStack need to look like in that kind of environment. And it's a little bit different than it may have been in the past with the other environments. And things are really changing fast, right? TAP didn't exist a year ago. So we realized that large regions that we've really locked in the architecture isn't necessarily what we want to do, because the bigger the ship, the harder it is to turn it, right? So we need a platform that can really adapt quickly, and we can change things. So from second generation to the new generation retains a lot of things. It's not, we're not wholesale changing out everything. We're maintaining the spine leaf network. We're using blades for compute. We're using that appliance storage, and continuing with the ironic deployments. I'll speed up a little bit.
Sure.
All right, but what are we doing? We're moving away from basically one big region per data center to where we can do smaller and variable size regions within the data centers. So we're changing the architecture a little bit so we can scale from one, we can be in one rack and call that a region, or we can go multi-rack and larger. We're containerizing everything, as I mentioned. We want flexibility around storage, so and I'll talk about that in a minute. I have another slide for that. We are looking at where does native Neutron fit now, as we're moving into Pike and Okata and things like that, and we're going to utilize service discovery more to really automate this more. So as far as release, as far as what we're deploying, we're moving away from the prepackaged, the RDO, RPM-based deployments to consuming Upstream directly from git.openstack.org. And the reason we do that is we like to own our own destiny. And we found oftentimes we're able to fix things faster than or when we need to fix things, right? We're not afraid of getting into the code and doing that. It allows us to pull updates and backport patches as we need to, and it gives us more confidence in the code that we're deploying. So we maintain a local Git repo for all of the Upstream projects, Nova, Neutron, Heat, everything. We have a Jenkins job that runs nightly. We maintain parallel branches, so from the stable Git branches upstream, we have a TGT target branch where we make our local changes, and then we rebase that nightly with the Jenkins job. You want to?
Yeah. Push that one. Do you want to talk about this? Yeah, so as far as CI/CD, this becomes important for us now that we're kind of sourcing OpenStack ourselves. Anytime we pull down changes and rebase our branches on stable branches, we need the confidence that our local branches aren't introducing regressions. So we run through all the PEP8 unit tests, et cetera, that you would expect to see upstream in the gates into the master branch or stable branches of the OpenStack code. Those end up getting published as Python wheels. They go out to a local PyPy mirror. So right now we're building Glance, Cinder, Keystone, Neutron, kind of anything that we might need to carry changes to, we're building that. And then build containers off those packages in our local PyPy mirror, and having that local has been real handy. That allows us to get around some of the challenges we all have around proxies, firewalls, as well as helps those builds go faster. It's an illustration of what it looks like. Mark mentioned we've got a nightly job that runs in Jenkins that rebases all of our local target branches on the upstream stable branches. We use drone to build, package, and push those artifacts out to where they need to go, whether that's a Docker registry, PyPy mirror, or even a Chef server for making changes to cookbooks. And developers interact directly with Git, and drone is kind of the tool of choice for kind of handling the gating and the testing and all that for us. So, as Mark mentioned, we're kind of moving forward, rethinking some of the things we've been doing with our current environment, which is kind of the second iteration. Funny enough, we call it Gen 3 target. What's a number? Some of the things that we've run into with a number of users are that they need their workloads to be directly routable inside of our data centers, hiding behind NAT or SNAT. So like a floating IP or just using SNAT out of a tenant subnet doesn't work. It tends to break tools like Consul and things that provide service discovery. So they need those workloads to be directly routable, and we've not had a good way to be friendly to those types of workloads. So we're thinking about some of the upstream stuff we get, like dynamic routing, and also subnet pools and address scopes, particularly subnet pools to be able to manage the address space that we get carved out from the network team. One of the things that's not there that I'd like to see that I never got around to doing was RBAC on subnet pools. Really having a tight integration there would help us a lot, so that we can kind of tightly control who accesses what blocks of IP address space, as well as maybe some enhanced quotas on that. But for the time being, our users seem to play nice and tend to be responsible, so that hasn't bitten us yet. So this is really experimental stuff that we're talking about here. A lot of this next generation architecture work that we've been pursuing is really fresh. One of the things, as Mark mentioned, we've been playing with is native Neutron. How can we make that play with a vendor solution that we've got? Where's the role for that? Is there one? And kind of the low-hanging fruit here to try out first was DVR. And it turns out that if you need to support some of these use cases, DVR isn't terribly far off from what you need. Some small customizations to the Neutron dynamic routing project allows you to be able to route tenant networks, expose them directly without sending that through the centralized router. So we can actually get full DVR in all cases with just a small change. And that's something I've been working on. I'd like to see that proposed as a spec and go upstream. The change is very small, but we'll see how that plays out. Key here is to reduce dependence on network nodes. Mark touched on that. Early on, we discovered that becomes a bottleneck and kind of a pain, and we really want that distributed routing experience. One of the key things that landed in the Pike release is DVR fast exit. So this allows the reason that you don't get the full DVR experience with Neutron dynamic routing is that until Pike and this fast exit functionality, the FIP namespace on a hypervisor wouldn't actually pass traffic unless it was going to a floating IP or it came through the centralized network node. Now with the fast exit functionality, you can route traffic directly to the hypervisor, and the FIP namespace will actually route that for you. That small change to Neutron dynamic routing in conjunction with DVR fast exit makes it possible with that fully routed experience. Obviously, there's known scale considerations with Neutron, and these are known with DVR. We're aware of those. As Mark mentioned, one of the things we're doing that mitigates our exposure there is smaller regions. So we're not growing to thousands of hypervisors in a region. We're keeping that rabbit infrastructure small. We know that RPC overhead associated with Neutron can be pretty heavy, as well as the north-south network traffic going in and out of the hypervisor instead of going through the network node. That helps a lot. Again, this is all very experimental. Tried this out on only a very small scale. So what does this look like? Your classic DVR picture, you got your FIP namespace. One of the changes, and I don't want to go too deep into it. If you're interested, I can talk your ear off about this stuff for for ages. But we do need to, for this to work in our spine leaf architecture, we have to play some games with Neutron because we've had challenges with the routed provider networks working with external networks. We pull an interface in, we've got the FIP namespace there, and we use Neutron dynamic routing through a route reflector to talk to the fabric. Kind of running out of time here, so go ahead and wrap it up. Future Kubernetes, GPUs, high I/O workloads. These are things that we want to support and be able to have land on OpenStack.
Yeah, around Kubernetes, Target is already using Kubernetes. We're still just kind of trying to figure out, how OpenStack and Kubernetes are going to live together. Is Kubernetes going to ultimately deploy on top of OpenStack or whatever?
Yeah. So with that, I don't know if we have time for questions. We're running a little over, but yeah, that's all we had. Thank you.